Hello?
Yeah.
Okay. Uh, it works, yeah.
Um, I don't know what's going on with.
Is there a call limit or
Let me see. It says. Um, Let me see. I didn't set any call limit or anything.
okay.
Let me check. Oh. I think there's a limit of about 9. Um, you can invite as many people as you want, but you cannot have more than 9 other people in a hangout at a time. I don't know what that means.
That's really weird.
Yeah.
Um, is there a way to edit that, do you think?
I can't. I don't really see a way.
Uh,
This is according to Google that there seems to be a limit. Um, yeah.
okay. Hmm.
Second we should do.
What?
I'm gonna. No, mine's not talking. It's off of yours.
Yeah, you're echoing off of me.
No, you're. Here's what you should do.
Wait,
I should
wait.
turn off of
I gotta
yours.
turn off my
Just-
mic.
Okay.
Okay. Let's see. Okay, because I'm echoing.
Professor?
Yeah.
Can you really quickly go over shear force? I know you're not gonna. I saw on the list of things you want to cover, but I guess
Um.
no one else is really asking questions.
Okay. What about it?
Just a really quick crash course in it, because my knowledge of shear force is not strong, and
Okay. So let's see. Let me get the book. Okay. Okay. Um. So there are essentially 2 or 3 different types of loading that you can have. Can you see? Can you see my paper?
wait, yes,
Okay. So there are basically 3 types of loading. You can have either tensile loading, which is like this. So you're basically pulling on a rod, or you're pushing on it on both sides, like that. Or you can shear it, and shearing basically means like this.
okay,
Okay. So you're basically trying to rip it apart by sliding along like that.
okay,
So this would be this kind of stuff. I'm at this point pulling on this, or I could push into it, or I could do that. If I do that, it's shearing.
okay.
Okay. This is the shear. This is shear forces. So let's look at some figures from the book, so you can see whether it is tensile, and just tell me whether it is in tension or shear. Okay. So this example here, is this focused enough for you?
Not really.
Um,
Let me, yeah, I mean, it looks like it's a U pin, right?
yeah,
A bolt. So
yeah,
then, wouldn't that not is the top of the bolt that's on that object, is that pushing down on it? Okay, so that would compress the object inside the bolt.
yes. So the object would be compressed. That's correct.
Okay.
Um, Let me. Well, you give me 1 second. I don't know where my little. Um, uh, I'm sorry. I'm just waiting to see if I can focus a little better on this.
It's okay. All right, I gotta mute this for a sec. Dude, I'm gonna take a fucking. Huh? Might as well. The cat's out of the bag. I gotta fart.
Oh my god.
Well, I mean, they're probably
Okay.
wondering if the wolves have descendants.
Okay. So this. So when you tighten these bolts here, this is like a U bolt. So when you tighten these bolts, what's going to happen to these blocks? Are they going to be compressed or stretched or sheared?
Compressed.
Compressed. Okay. What's going to happen to the bolt? Is it going to be stretched or sheared or compressed?
Compressed.
The
Well,
bolt.
because isn't it just going straight down? Isn't it?
So when you tighten this, it is the bolt will be pushing down upon these blocks.
Right.
What are the blocks going to do to the bolt?
They're gonna push back.
They're going to push back, which means that this is going to be in
tension. Yeah.
that's going to be in tension. So the bolt itself will be in tension, but this will be in compression.
Okay.
This will be, so let's look at another one. Okay, let's look at this picture here. So it's a wire cutter, and there is a wire here, and you're pushing down upon this to cut this wire. So when you look at this picture here, this is the cross-sectional view of the pin. There's the pin that goes through that, and this part is one of these, and the other one is the one behind it. Okay. So now what's going to happen at the pin is that the pin is going to be pulled in one direction with 385 newtons and pulled in the other direction with 385 newtons. Now if you look at the pin, it is going to sail right along there.
Sorry, it's gonna what along that line?
It is going to be sheared along that line.
Okay.
Do you see that?
Yeah.
Okay. That again is shear. Let's look at this picture. So there is a force of 350 newtons being 350 pounds that's pulling on this bolt. What kind of force is going to be experienced by this part of the bolt or the rod?
Tension.
Tension. Good. Now let's look at this pin here. What is the pin going to be experiencing? The bolt is trying to push the pin like in that direction, and the pin is going to be under
Double shear, right?
And do you see why?
Yeah, because the part of the bolt that's like a U is gonna be pulling up on both ends, while the other part is gonna be pulling down on it.
Yeah. So it looks something like this. And then there is the rest of the threaded rod up there. And then if I draw just the pin, then the pin is being pulled in that direction by this threaded rod and is being pulled down by the bracket.
Okay.
It's being pulled down by this bracket here. Right?
Yeah.
So here, this is the area that we're talking about.
Mm-hmm.
And so the force is parallel to this area.
Okay.
So in shear, the force will be parallel to area over area, and in tension or in compression, it'll be the force will be perpendicular to the area. Okay.
Sorry, does that say why do you have force parallel to area over
This
area?
is over area.
Oh no, why do you have it over the area though? Is it just
Shear stress. This is shear stress. Sorry.
But that's just for the sake of the equation though.
Stress is always force over area.
Right.
So the question is which force and what area.
Okay. Thank you.
Okay, so let's look at a few more examples of this then. let's look at this one. This is page 220 in the book. And there is a key here. So there is a shaft and then and a gear, and they're connected by means of a key. So here is a picture of the front view of it. So there is a 1,500-pound force that is acting in that direction. What kind of stress is this key experiencing?
Well, I know the book says it's supposed to be shear force, but I don't quite understand why it is shear force yet.
Okay, so if we have a 1,500-pound force here, what is the torque on this?
So I mean 1,500 times the radius.
1,500 times the radius, that's the torque. So if that is the torque, then what is the force experienced by this key?
Wouldn't it be the torque?
No, the torque is not a force.
Okay.
So here is the 1,500-pound force, and here is the key. So this 1,500-pound force is, what is the force on this key now?
Oh, it's tension because it's perpendicular to the key.
Okay, so how is this? How do you suppose this is going to fail? Let's say this were going to break. What direction would it break in?
Parallel to the force.
So which direction? So let's say here is the key. Here is the key, and here is the shaft that's going through it. That is, I just do this. Is it going to fail like this, like this?
Second option.
Second option is going to fail in that manner, right?
Yeah.
What direction is the force?
Parallel to that. So
that's why it's shear.
Okay.
And now you need to make sure that you're taking the force that is parallel to this, right?
Okay.
Got it?
Yeah.
Okay. Now let's look at a few more. This one. What is the force acting? What is the kind of stress that is acting on this part of the bolt?
Tension.
Tension. It is part tension because there's one part of it that is pulling up, and there is another part that is parallel. This is the force is at an angle.
Yeah. So. Yeah.
So it is both tension and shear. Right?
Yes.
So the component that is along the bolt will be pulling it straight up, and the force that is perpendicular to it, that is along this one, would be shearing it.
Yeah.
Okay. What about this one?
What are you asking about? Where
we're talking about this pin. We're talking about this little link here. A, B.
It would be sheared.
Link. The link will be sheared?
Oh, sorry. Tension, because or compressed.
Yeah. Tension. Because when you pull on, when you press on this is going to be pulled apart. A and B are going to be pulled apart.
Oh. Okay, yeah, then it's being able to put tension.
What about these pins? These pins here. What like this pin here and this pin here. What about that? Them. Would they be sheared or in tension or compression?
Sheared.
Sheared, yes. All right, let's do this. So you have a blade, a saw blade, and it's being pulled by force P.
Tension.
Tension. And what area are we looking for? So here are the dimensions given. It's 3/8 inch wide, 3 inches long, and 0.025 inches thick. So which area should we be looking for?
I'm sorry. One more time.
So the tensile stress is going to be force over area. So which area? There are 3 dimensions here.
Wouldn't you want the area of the object?
Yeah, but which area?
I guess just a part of the blade, just the face of the blade.
Face meaning which? So tell me, what is the area?
Is that 3/8 inches right under P?
Sorry, 3/8 inch and
And the 3 inches for the length. That'd be the area you
no.
want.
So this will give you this area.
Yeah,
If you
that's
do, but that area is not perpendicular to the force. It is this area that you want, the cross sectional area, which is 3/8 times 0.225.
okay.
Do you see it? Like, let me draw it here. Here is a blade. So this is 0.025. This is 3, and this is 3/8, and it's being pulled like so.
Okay.
So the area that we want is this area here, the sectional area. Right? Because that's the area that's perpendicular to the force. This area is not perpendicular to this force.
Okay. I get it now.
Okay?
Yeah.
Okay, then do this.
Give me 1 second so I can. What page of the book is it? I just got a book. What page is it on?
231.
231. Would it be? Well, part of it would be compressed, and the other part would be tension, right?
Sorry, which? One second. Oh, give me one.
Oh. Never mind. What?
So what is the kind of force on this part?
Where it has the 6 millimeters?
Yeah.
Wouldn't it be tensile because it's being pulled?
Yes, that's tensile. And what is the force on the bolt? What kind of force is it on the bolt?
It'd be shear.
Shear. Good. And single shear or double shear?
Double shear?
Single, because it's only shearing along this one plane.
Okay.
Okay.
Thank you.
What about this? You're looking at the rivets.
It'd be shear?
Yes, shear. And so, because this is a 600-pound force, that 600-pound force would be divided among these five rivets. There are 5 rivets, so each one would carry 120 pounds.
Okay.
Okay. What about this?
Shear stress for the bolt, right?
Why
Yeah.
is it shear again
Where?
in the rivet?
In the rivet? Because if you look at this picture,
Yeah.
it is being pulled up. This is being pulled. This part remains stationary. This is the lower part that remains stationary, and this other one is being pulled up, and the rivets are joining these two.
So the force is perpendicular?
No. No, hold on. Hold on, one second. Let me get a pencil so I can write on this. Okay. So this is this piece, and this one is the other piece. Okay.
Okay.
So this guy is pulling up with 600 pounds like that, and
Mm-hmm.
this one is restraining it with 600 pounds pointing down. So that this plane here, which is the joint between the two, is being sheared.
Oh, okay, okay. So the area you use is not is the one like that you can see directly.
No, yeah, it's this
It's
area.
this, yeah, not the other. Okay, I get it now. Okay, thanks.
Okay, try this. I'll be back in a second. Give me about half a minute. I'll be back.
Isn't this one both?
Hey, Karn.
Yeah. Doesn't carry out what the? Isn't it both in this case?
For what?
Like which kind of stress it is on the circled thing?
Are you talking about 522? Or the one he was drawing on right now?
No, the one with like the triangular thing.
Oh, the one with the rings?
Yeah.
Okay, what was your question one more time?
But like is it shear or tensile? It's both, right?
I think it'd just be sheer. I mean, yeah, it's both actually.
Wait, someone else is trying to talk and it's like echoing. So does anyone know?
Sorry, I'm trying to fix the echo.
Okay,
I'm back. Sorry.
Yeah, is it both?
Sorry?
Is it both? Because the force is at an angle?
No. We're talking about just this part.
Oh, sorry. Okay, so is that gonna be shear?
Yeah, that is straight. This is just shear.
It's just straight down, right? Yeah. Okay.
Yeah. And it's double shear, right?
Wait,
Because
why?
these two.
Oh, okay, I see. So when it's double shear, you half the force, right?
Yeah, if the force becomes half, one half here, one half there.
Okay, cool, thanks.
And what about the force? What about the force on this thing? What kind of stress does this have on this?
It's the forces are parallel, right?
Yeah, the stress. Yeah, the force is parallel here, like this. So what is this kind of force?
Tensile?
Yeah, this is tensile.
I think the echo's fixed.
Not really, dude. Okay, so shear is always when it's perpendicular, you said?
No, shear is when it's parallel, like
Parallel.
this.
Okay. Yeah, okay. So and then, so in the case of the rope, it's tensile because why?
Wait, I'm getting a lot of questions. Hold on, 1 second. Where my homeworks are.
Is it better now?
No.
Yeah.
Okay, it's fixed.
No.
Actually, I had the same question as Richard. I don't know if you saw it.
Why is it?
Multiplied by sine and cosine.
Yeah, hold on. Okay, I don't know where my problems are, but I think I remember what the question is. In that problem, you had it was a wooden beam, right? Is that the one?
Hang on. 11. Yeah, it is that one.
So it is being cut at 45 degrees, right? In part
Yeah.
C.
Yeah,
So
that's right.
So when you have a force like this, then you have to resolve this force into two parts.
Wait, where is that force coming from?
That's an internal force. So when you cut something, when something is cut, it still has to be in equilibrium. Therefore, if you have a force here, there has to be a force here. Otherwise, this won't be in equilibrium anymore.
Wait, where's the force? Oh, you mean the reaction force on the other side?
There is a force on the beam, right? I think it's compressive or something. I forget what it is. Is it compressive? I don't have the problem in my hand. That's why I cannot tell you exactly what it is.
Okay.
Is it a compressive force?
I'm just gonna look at it again. So wait, is there screen sharing on this? Let me show you the problem.
Yeah, I think if you turn on the camera, you could just bring it up and it'll focus.
I'll show you the problem.
Was it 11?
Yeah.
Is that? No, it's 12. Set. No.
Okay, so it's a wooden beam supported by a rope,
Mm-hmm.
and so there's the beam. It's OB. O is supported against the wall,
Mm-hmm.
and then there's a rope connecting B to another point on the wall with a mass hanging from it.
Right.
And it says that the wood beam breaks while shipping, and then the construction worker cuts the beam at an angle of 45 degrees, and glues the pieces with an adhesive that can withstand a shear stress of 44 megapascals.
Professor, real quick, you have a limit on how many people can join the chat, by the way.
I didn't do anything. I think there's a limit by Google.
Oh, okay.
I think there's a limit of 9, but I don't know. Okay, can I just check? Give me a second. Let me just check.
Okay. Well, I'm currently in the discussion, so I'll just listen from right here or type.
Like how he admit. Your shit.
Add up all the Y components. Okay.
I think.
Yeah, go ahead.
Hello?
Yeah.
Did you manage to find it or solve it?
Well, I think okay. Let me just give you the link to the events because I think it says that there is a limit, but there is something called Hangouts on air, which I don't know what that is.
Okay.
It's basically you can't talk, but you can watch.
Oh, I see. Okay.
Oh, that's.
But how do you get to it?
Hmm.
I think you can like access it using the same link.
Okay.
Let me try it.
Con, what number are you on for the homework? Are you on 11 too?
Huh?
Are you on number 11 for the homework?
No, I got ahead of that.
Oh, okay.
So you got this problem?
Well, I just don't understand where the sine and cosine part come from.
Okay,
Like, as
so
in,
there's a P here, right? You get this? There's a P
Yeah.
here and a P there.
wait, why?
Because anytime, I mean, you can cut this beam at any point like this. You can
Okay.
cut it at any plane, and every plane, every piece of the beam has to be in equilibrium,
Okay.
which means that there have to be equal and opposite forces on both sides. Otherwise, they'll start moving.
Oh, okay. I see.
These are internal forces.
So
So
P
you
goes.
have a force here, P, and then there is P this way too.
Oh, okay. I see. So P is the normal from the wall, right? In your case?
And you have to do
Yeah, it should be the compressive force over there.
Yeah. Cool. Okay.
Oh,
Then you can resolve this into sine and cosine. But once you resolve that, so this is, let's say this is theta. If that is theta, then I believe that this one is 2.
Yeah.
This one is 2.
Yeah.
So that this becomes P sine theta, and this is P cosine.
Okay.
Now this, if this here is if this area is A, then this area is, if this is A, then this area is A over cosine theta.
Yeah.
So that the compressive force sigma C would be P cosine theta over A over cosine theta. So it is P over A cosine square theta. And tau would be P sine theta over A over cosine theta. So P over A sine theta cosine theta.
Oh, okay. I see. Okay, fine. That makes a lot of sense.
okay.
Okay, thanks. Kind of get it now. Is this what the quiz will be on tomorrow? Stresses?
Yeah,
Is there
stress.
quiz
There'll be one stress problem and one problem on the what's that? Pressure.
Oh, okay. So in fluids, right? Okay. So,
Okay, so there is a quiz tomorrow, though?
Yep.
Okay.
Can you make up a question that makes sure we know how to like go about the problem?
No.
Why?
Go do the homework. It should be one of those things.
Okay, sure. Let's go through that.
Okay. What else? If there's someone on here who is not on the Hangout, can you text? Can you use the text? Does it work? So just text me. I'll know. No, but Anthony, I think you are on Google Hangouts. I'm saying if there's someone not on here but who's able to just listen or watch it.
I don't think their thing will come on message. I think they can post.
Huh?
Like so, when it's on air, there's like this like board that you can post on, and you can just post on there. But I don't know how to access it. So.
But Jose is being able to post. I think. just want to make sure that he is because I see some of his questions, but he's not on here. So I was just wondering.
He is. He's on the Hangout.
Oh yeah, that's him, isn't it? Okay, yeah.
Yeah, the guy with the weird face.
Yeah. Right.
Yeah.
Okay, what's the difference between gauge pressure and absolute pressure? Oh, gauge pressure is when you okay, absolute pressure is simply the total pressure. This or absolute pressure is the atmospheric pressure plus the gauge pressure. So so gauge pressure is simply absolute minus atmospheric. Okay. So let's do a simple example of this. So let's say you have a tub of water which is 5 meters deep. So and the pressure above this is say atmospheric. So the question is, what's the pressure at the bottom? So what's the formula for PA?
Are you talking about absolute pressure or gauge pressure?
Give me any.
Oh, so it's hang on.
Sorry?
Yeah.
Is it like rho GH?
Yeah. So wait, is it absolute or gauge? What are you doing?
Gauge.
Okay, let's do absolute then.
Okay.
Absolute pressure is this pressure plus whatever is here.
Yeah. Okay.
So it's
So
P
that's
atmospheric.
P atmosphere plus rho GH.
So it's P atmospheric plus H, which is 5, rho is 10 to the 3, and this is say 10. So
Yeah.
so this is P atmospheric plus
5
50
times 10 to the 4.
kilopascals. 50 kilopascals.
Cool.
Okay. So if you wanted gauge pressure, it would simply be PA minus P atmospheric, which is 50 kilopascals. If you want absolute pressure, it would be P atmospheric plus 50 kilopascals. This is gauge.
Yeah.
And if you want absolute pressure, it would be 101.3 kilopascals plus 50 kilopascals, which would be 151.3 kilopascals.
P atmospheric is constant, right?
Huh?
P atmospheric is a constant, right?
Yeah, P
101.3.
atmospheric is 101.3 kilopascal.
Right.
Is that clear? Richard, the person who asked me the question. Yeah, good, thanks. Okay, then why don't you try one of those problems from the homework that had to do with these pressure problems? So for example, try problem 16. Got it? The pressure at the bottom is equal to the pressure through the tube. Oh, how do you mean through the tube? Again, that's not clear. I don't understand what that means. The pressure that the water is being pushed through. Well, I mean, pressure is equal at some point. You need to pick 2 points at which you can equalize the pressures. So for example, you can choose a point here and a point here. So these 2 points will have, like, if we call them A and A prime, then the pressure at A will be equal to the pressure at A prime. So what is the pressure at A? Why P atmospheric? This is not exposed to atmosphere here. This part is not exposed to atmospheric. Just look at this part first. Oh, you're doing it for the other one. This is PA prime. Okay, this is correct. P atmospheric plus rho GH. That is for this side. What about for this side? Yeah, but that's not. It's not just quite 40 kilopascals because this is gauge pressure. So if you want to do the actual pressure, it should be P atmospheric plus 40 kilopascals plus rho GH plus rho G times 2. That's why this is gauge pressure. See, that's why it's gauge. So you need to add the atmospheric pressure for this. Okay, so if you do that, then you get P atmospheric plus 40 kilopascals or 40 kilopascals plus rho GH, rho G times 2 equals P atmospheric plus rho GH. So that goes away, and here you have 40,000 plus rho, which is 10 to the 3. G is 10 times 2 equals 10 to 10 to the 3 times 10 times H. So this gives you 4 plus 2 equals H. So H is 6. Good. If you're done with that, then try problem 17.
Professor, could you explain 16 again?
16, the same one that we did?
Yeah.
Okay. So let me draw this again.
Are you talking about 16 on the homework?
Yeah. So this is 40 kilopascals gauge, and this is given to be 2, and we're asked to find what this H should be. So in these problems, you always have to find a level at which you want to find pressures, where you can equalize the pressure. So you can choose this point and this point, for example. So so let's call this A and A prime. What's the pressure at A? And so the pressure at A and pressure at A prime has to be the same. These two are the same level, so they have to have the same pressure. What's the pressure at A? Whatever is above point A. Look just above point A.
Is it rho GH?
And what about this?
Do you just add that pressure?
Yeah. But this is gauge, so you have to add not just that, but also atmospheric. So if you're given gauge pressure, you have to add atmospheric pressure to get the absolute pressure.
Oh, what was the formula for absolute pressure again?
It's gauge plus whatever pressure you have.
Okay.
And then we just use that formula to get the answer.
Yeah, so this is pressure at A, and this H is 2, okay? And then what is the pressure at A prime? Just look above that. What's above that?
Rho GH.
Plus. And what's above that?
The the absolute pressure.
Atmospheric. Atmospheric, right? There's nothing else. It's atmosphere.
Oh, okay.
So that goes away, and so then you solve for it, you get 6.
So what exactly is gauge pressure?
Gauge is the difference between the absolute pressure and the atmospheric pressure. I mean, it's kind of circular all over the place, so you have to pick one. I mean, absolute pressure is basically force over area. Let's start with there. Absolute pressure is force over area. Okay. And if you subtract out the atmospheric pressure, you get gauge.
Okay.
So the gauge pressure for the atmosphere is 0, because atmospheric pressure minus atmospheric pressure will give you 0.
Okay.
Okay.
Okay, thanks.
So then try the next problem. I think this is problem 17. Okay, so as Richard said, if you take the pressure at these 2 points, say C and C prime, then the pressure above C prime is going to be PA plus the column of water, which is 3 times rho times G, and then the pressure at C prime would be the pressure of the column of water above that, which is 4.5 times rho times G plus the pressure at B. So that you get, if you know this, then you can compute what this is. You don't have to go all the way down to C. You can also just go here.
How come? Sorry.
Uh-huh.
How come for the rho GH in the first equation you use 3 instead of 2?
Yeah, but I think there's a mistake on the figure. It should be 3.
Oh, so you're using the 3 for the water?
Yeah, this one is 3.
Okay.
Yeah, right.
All right, just checking.
Now, what would happen if I chose this here, D and D prime instead?
I'm sorry. Is the first D level?
Yeah, the D right at the level and D prime is at the same level on the other side.
The pressures would be equal.
Correct. And so, what would be the formula? What would be the pressure at D?
It would be the same as D prime.
No, yeah, that's right. But just look. Yeah, that's correct. But then now, what is the pressure at D?
It would
You need a formula for it.
the
So
pressure.
just above it. What's the pressure above?
Sorry?
What's the pressure above D?
Wouldn't it just be the pressure from A, the air pressure?
Yeah, that's it. Now, what is the pressure from D prime at D prime?
PB, or the pressure of point B?
But that is here. Plus, there is this column of water.
Oh, 1. H should be 1.
It should be 1.5.
Wouldn't it be 1?
This is 3, so this is 1.5, so this would be 1.5.
Yeah, it would be that height.
This height.
Yeah.
Yeah, there you go. They'll both give the same answer, obviously. See, because if I take this over to the other side, I'll get 1.5. Right?
Yeah.
Okay. Good. Now let me give you a different problem, so you can solve something else. Give me 1 second for this. It's not totally clear what this problem is asking, so sorry. That's not okay. Okay, this is okay. So this is mercury in here. What's the pressure at A? So this is mercury, and this is water.
Professor?
Yeah.
What is the density of mercury?
13. Specific gravity is 13.6.
Thank you.
You don't need this. You don't need Z. If you're done with that, do this one. P equals P atmospheric plus 13,600 times 0.3. So did you guys finish this? Okay, let me do this. So let's take the pressures from this level. So let's call this A prime. So the pressure at A would equal pressure at A prime. Okay? Now, if the pressure at A is equal to A prime, then what's the pressure at A? Sorry, this is already A, so let's call this B prime. So the pressure at B equals pressure at B prime. So the pressure at B would equal, on this side, on this leg, would equal the pressure at A plus this height. And now if I cross over to the other side, I get the pressure of atmospheric plus all this stuff, which is 10 plus, so density of mercury plus G. So the pressure of A is pressure of atmospheric plus 0.3 times rho of mercury times G minus 0.1 times rho of water times G. Okay, so it will be P atmospheric plus 0.3 times 13,600 times G minus 0.1 times 1000 times G. Okay, so yeah, you have to take, if this were air, if this instead of water, this is just air, then you would be correct. Then you just have this term because the density of air is much lower than the density of mercury. So the height of this column makes no difference for air. But if it's water, then water is definitely dense. So you have to include that in the calculation. Okay, then try this one.
Hey, Professor, I had a quick question on E problems. When you're solving for the remaining mass, like after it's gone over 100 degrees Celsius,
Yeah.
would you divide by the latent heat of vaporization plus the amount of energy it takes to get to 100 degrees Celsius, or would you subtract the
I
amount of
know. I have no idea what you're talking about, but let's do. You need to do the whole problem. Let me. Can. Okay. Um, can I answer that question in about 5 minutes? Let me finish this and then we'll get to that. Okay.
Okay, sounds good.
Because then I have to remove this piece of paper and then I cannot do that. Okay, I'll be back. Okay, give me 2 minutes. Meanwhile, I'll finish solving the problem. Let me see if I can get the icons off. Yeah, I don't know how to do this. Yeah, I know it's kind of annoying. I mean, it takes up half the screen, but I have no idea how to get rid of it. Sorry. Okay, so how do you guys do it? What atmospheric pressure? There's no atmospheric pressure on which side? This is P air. This is not open. This is open. Just write out the equation so that we can move on and do. So, so can someone tell me how to do this?
Okay, so would you for the mercury part of it, would you draw a line, the part where you like put a line through
Yeah.
that
So where would
thing?
you put the line?
Huh?
Where would you put the line?
The that little line you put,
Here.
like, yeah, that like
Okay.
to the right hand side, you cut it off.
All right. Good. Let's call
Yeah.
this B prime. All right.
Yeah, and then for the B prime part, it would be atmospheric pressure, which is 0, right?
If
Plus
you
rho
put
GH.
atmospheric pressure equal to 0, then you're doing gauge. Okay. You can do it that way. If you want to do it with atmospheric 0, then you can, but then you need to keep in mind that everything that you're going to get is in terms of gauge pressures. So that's fine. You want to do it that way?
Wait, what do you mean by that?
If you set atmospheric pressure equal to 0,
Uh-huh.
then you're working with gauge pressures. Then every answer that you're going to get is gauge. Is going to get gauge. So when you get PA finally, it'll be gauge pressure. Otherwise, it'll be absolute. So you kind of have to make up your mind whether you want absolute pressure or gauge pressure.
Oh, okay. I'll do absolute pressure then.
Okay, then you need to throw in atmospheric.
Okay, atmospheric plus rho GH.
And rho H being
H is 0.3.
0.3 and times the density of mercury times G. Okay.
Yeah.
What about on the other side? This one.
And the other side, it's the density of water, which is 1,000, plus gravity plus
times
times the I was confused about the height part.
What is the height of the water column? It's what is the height of water above that point?
0.3.
No, what 0.3? This is mercury. This is water.
Wait. Wait, the height of where?
This is water. What's the height of water above this?
Isn't it 0.3?
Why? How 0.3? 0.3 is this side. You're done with this side. Forget this. Now you're coming over to this part.
Oh. Is it what Richard said? 1.6?
Yeah, 1.6. So this is 1.6.
Oh, so we don't have to find the height of the whole water part.
What whole water? There's only this much water from here to here.
Oh, I thought it goes down.
Yeah, but that doesn't matter. Water, the pressure only depends upon what's above, not below.
Oh, okay.
Remember, where is pressure coming from? Pressure is a gravity effect. So it
Yeah.
only depends upon, it's like if you are standing on top of a building, the only thing that matters is what's on top of you, or if you're in a human pyramid, right?
Uh-huh.
And what matters is who's above you. Who's below you is not a problem.
Okay. Okay, so rho GH plus well, you know specific gravity of oil, so you can find the density of the oil and times the gravity times 3 meters plus the absolute pressure.
Point A, right?
Yeah.
Yeah, there you go. That's it. Then solve it. Yeah. Solve it for you. You know everything else.
Okay.
Okay? Good. So now let's move on. Let's talk about one of the problems that who had? Amir had on this. Can you see this? Oh, why is it going all the way up here? Okay. So this is a thermal problem. So kettle of water containing 2 liters of water is kept on an electric heater, and it supplies 500 watts. The heater is kept on for 5 minutes, and then we want to find what the final state of the water is.
Professor, I have a quick question.
Yeah.
So, in some of the problems, you use the specific heat of water to be 4.2, and in other ones you use 4200. How do we know which one to use and when?
They're both the same. One is 4200. It is 4.2 kilojoules or 4200 joules.
Right, but when I used one, I got a completely different answer than when I used the other one. So like.
Of course, but I mean, if you have to make it consistent. So if everything is in kilojoules, if the entire problem is in kilojoules, then you can just use kilojoules directly. 4.2. If some values are in joules and some are in kilojoules, then you have to convert one to the other one to the correct form, right?
Okay.
Most of the time, we remember it in the form 4.2 kilojoules per kilogram Kelvin.
Okay.
Okay. Do you see how the units work out? See,
Yes.
because if everything is in kilojoules, then it makes no sense to be converting it to joules and then converting back to kilojoules and all that. So you just keep everything in kilojoules. Okay, we'll do this. Oh, we need the initial temperature of water. Let me.
Professor,
Yeah. Yeah.
would we convert the time of 5 minutes into seconds?
Yeah.
Okay. And then we divide that by the watts to get the big joules. And you can use that to solve for temperature.
Divide.
You divide the watts by the time to get joules.
What is watts? What is what? What is watts?
The power supplies by the electric heater. Oh, multiple? Oh, you're right. It's multiply. Okay. Sorry.
Got it? So how much heat are you supplying total? Okay, somebody walk me through the solution for this. Yes. Uh-huh.
Would you use Q equals MC delta T?
Yeah, because it's at 50 degrees. So we have to use equivalent T first.
Okay. So you find the mass,
Mm-hmm.
and then you know the specific heat of water.
Yeah. What is the mass?
Oh, the mass is 10,000.
2 liters. 2 liters will be 2 kilograms. It's liters.
Oh. Oh, what do you convert liters to for volume?
Meter cube. What's the density of water?
1,000.
Or what? What's the units?
Kilograms.
Kilograms meters cubed.
Or it is 1 kilogram per liter. Either one.
Oh, okay.
So walk me through the process, Suman.
So you're gonna take the 500 watts,
Yeah.
multiply that by 300 seconds to get it, and that's gonna be times. It's gonna be 150 kilojoules.
Correct.
Let's set that equal to the equation MC delta T.
Mm-hmm.
The mass is 2 kilograms.
Mm-hmm.
The C is 4.2.
Mm-hmm.
And the delta T is going to be 50 minus T.
T minus 50.
Oh, yeah. And then You're gonna distribute you're gonna multiply 2 and 4.2 together, and you distribute that to the third term of the equation.
No, just do 150 over 8.4.
Or you can do that too.
Yeah. Uh-huh.
Well, 17. I got 17.9.
Okay. Okay. So that's like, so the temperature comes out to be something like, so what's the final temperature of the water?
67.9 degrees Celsius.
Okay, so it still remains water, right?
Yes.
So how long does it take to reach boiling point?
A while.
So you figure that out.
Damn it.
So from 68, so it's now at 68. So how long do we need to leave the heater on?
You basically use Q equals MC delta T, except this time your delta T would be 50. And then
68. Oh, yeah, okay, fine. Okay, fine. Fine. Go ahead.
and you get 420 kilojoules. And then fuck. So I had like an interesting idea on how to get the time. So with the heat, I took the 420 divided by 150 to find the ratio, and I multiplied that answer by the minutes to get
Wait, what? Say that again?
minutes to
Say
boil
that
the
again?
water. I got 14 minutes to boil the water.
To get it to boiling point?
Yeah.
From 50 degrees Celsius?
Yeah.
Okay, so let's see. So how much heat would it take to boil the water from 50 degrees?
420 kilojoules.
So 2 times 4.2 times 50, right?
Yep.
So 420 kilojoules.
Yes.
And you're supplying at the rate of 0.5. 0.5 kilowatts per kilo, sorry, 0.5 kilowatts per second is what you're supplying, or kilojoules per second is what you're supplying. 500 watts, right? That should be 840 seconds, or 840 seconds would be 14 minutes. Is that what you said?
Yeah. I mean, I got my answer a way different way, but
Okay, what did you do?
I took the energy required for this equation, and I divided that over the equation for the energy from the other equation. So 420 divided by 150, and I took the answer from that and multiplied it by the total time to get 14 minutes.
Okay. All right. I mean, the simplest way to do it is to say, okay, how much energy do I need? I need 420 kilojoules. How much energy am I supplying per second? 0.5. If I'm supplying 0.5 kilojoules per second, then how long would it take me to supply 420? And so it'll be 840 seconds, right?
Yes.
Okay. So now let's say that I leave the heater on for half an hour. So starting with water at 50 degrees. How much water would have boiled?
Yo, Hang on, let me mute this for a sec so I can talk to you.
Point 0.21, 0.5 times 1800. 1800. So let's see. Yep, correct. Good. And how long would it take for all the water to boil off? Yeah, good. So does everyone understand the logic of this?
Yeah.
Are there any questions on how to do these things?
So you can always multiply Q by T so that you can find time, right? Or could you just divide it without including the T?
No. I mean, I don't know what you're talking about, but don't think about it like multiplying and dividing. If you're supplying a certain amount of energy per second, and you want to find the total amount of and you want to find how much the total, and you're given a certain amount of energy that you need, then obviously you have to multiply the amount of energy per second times time. That'll give you the total amount of energy.
Yeah.
Right? Yeah.
Yeah, you're right.
It's not about whether it's always this or always that. I mean, it depends on what you want.
All right.
Wait, could you show how you got the answer?
So which one? This one or this one?
The first one.
This one?
Yeah.
How much water would have boiled? Yeah. So so how much heat are you supplying in 30 minutes? So heat supplied is going to be the heat gained by water, right?
Yeah.
So how much heat are you supplying in 30 minutes? So you're supplying 0.5 kilojoules per second, and it's 30 minutes, so it's 30 times 60. So this is how much heat you're supplying.
Okay.
How much heat is gained by the water? First, it needs to go into boiling. So it is 4.2 times 50. This is MC delta T.
Okay.
We already figured out that if you keep it on for 14 minutes, it will hit boiling. If you don't know that, then you just do MC delta T, and you'll find the delta T you'll find the T comes out to be more than 100. And once you figure out that T is more than 100, then you know that it's boiling. So this formula is no good. So you have to use MC delta T plus some mass times the latent heat, which is 2260 kilojoules.
Okay.
Okay. And then you'll find some fraction M. If you solve this out, you'll get M.
Oh, okay.
Oh, that's to find how much mass was boiled?
Yes.
Or how much water is boiled?
Yeah.
Okay. Will this be up on YouTube soon?
Yeah, I mean, it goes up automatically. I don't do anything. So it takes a little bit, like maybe half an hour or so, but yeah.
All right.
Okay.
All right. Thank you, Professor.
Yeah. So what I want to do is now review some of the, the last 3 or 4 problems from the additional problems in Newton's laws, the mechanics problems. There were about 3 or 4 problems from law of conservation of energy that I want to review.
All right.
And then I don't know if we have time to do heat transfer, but do you have any heat transfer questions?
Yeah.
Okay, go on then. Let's do that first.
So for on the last quiz, or not the last quiz, a couple quizzes ago,
yeah.
It was quiz 6, I think.
Okay. What about it?
Through a material being equal to Q convection and Q radiative.
Yeah.
How are you supposed to know that its conduction equals the other two, and not the other way?
I mean, I think what was given in the problem was that you had a wall. This temperature was given, right?
Yeah.
And this temperature is given, correct?
Yes.
And the ambient temperature is given. Is that right?
Yeah.
Okay. So in these, so what's happening is that there is heat that is flowing through the wall. So how is the heat flowing through the wall? What mechanism is it? Conduction, convection, or radiation?
Conduction.
So it's conduction. So it's flowing through conduction, and once the heat hits the outer wall, how is it going to get out?
Convective.
And
radiative.
Also radiate. Okay.
Yeah.
Okay. Now, if Q conduction is greater than the sum of these two, what's going to happen?
If it's
If
greater,
more heat is flowing in than that's coming, than that is able to flow out, what's
then
going to happen to this wall?
it's staying inside.
Heat cannot stay inside. There's no such thing as heat. Heat is only in transit. Heat can only move through. If it stays anywhere, what is it going to do?
It has to go to a lower temperature.
No, it will heat up. It will heat something up.
Okay.
If heat has nowhere to go, like if your house is on fire, what's going to happen to the house?
It's gonna catch on fire.
It's catch on fire, but what happens to the temperature?
It goes up.
It goes up. If that heat is able to escape, then your house remains cool, right?
Yeah.
It's the same thing. So if heat piles up somewhere and is not able to leave, then this wall is going to start getting hotter and hotter.
Uh-huh.
Likewise, if Q conduction is less than these two, what's going to happen?
It's gonna all go out.
No. If the amount of heat conducted to this wall is less than these two, then the sum of these two. So there is more heat that is leaving than that is entering the wall. What's going to happen to this? The temperature here.
It's going to go down.
It's going to go down. You're right. That's kind of what happens when you have a hypothermia. There's too much cold outside, so the temperature of your outside starts dropping, and there's not enough heat from inside that is able to come and catch up with it. So you start getting colder and colder, and you start getting into hypothermic shock. That's exactly what happens. So basically, if you want to have a steady temperature of the wall here, the heat that is coming through conduction must equal the heat that is being conducted and convected and radiated.
And that's what's called a steady state.
That is steady state. Steady state means the temperatures remain steady.
Okay. Do we have to know how to deal with unsteady states?
No.
Okay. All right.
How does it also get out by radiation? Because there is a temperature difference. There is no material. There's no solid material, so it can radiate. Do you get it?
Yeah.
I mean, if you stand in front of a stove, for example, like a gas stove or an electric stove, you feel hot, correct?
Mm-hmm. Yeah.
Why do you feel hot?
Convective heat transfer? No. Radiative.
Convective. There is convection going on too, because the gas will heat up the air, and the air will comes in contact with you and heats you up. That's one mechanism. But the other mechanism is also direct heat transfer through radiation.
Okay.
There is also direct transfer. So it's both mechanisms together. Okay? That's why you get that equation. Now, what would happen on a very hot day? Let's say it's a very hot day outside, and this temperature is 45 degrees Celsius, like in Palm Springs. And your house is being kept cool at 15 degrees Celsius. Then how is the heat going to enter your house?
From the outside in?
From the outside in, correct. And then, so what mechanism?
Conduction first.
Through what?
Through the wall.
How is the heat?
Convective is going to heat up the air of convection is going to heat up the wall.
And
then it's going to go through as conduction.
Correct. So there is convection from here, and then there is conduction here. Is there radiation as well?
From the sun.
Yeah, or even from air. Air can also radiate. Both can radiate. You can have radiation and convection. So in these kinds of problems, sometimes it'll tell you, I mean, I'll explicitly tell you, neglect radiation or neglect this or neglect that. And unless it says that, you cannot neglect it. And especially if in radiation, you'll be given the emissivity. Typically, that's a dead giveaway for radiation.
Yeah.
Okay. So conduction, for convection problems, you must be given the heat transfer coefficient, or convective heat transfer coefficient is typically given.
So if you wanted us to figure out like the radiation of air, would you give us the emissivity of air then?
The emissivity of the surface, not air. Air is
The surface.
This is the surface, yeah. Like in that problem, in that quiz, you're given it as 0.85 or something.
Yeah. Thank you.
Okay. So do you understand this part, like how these things work? Like if I have a sandwich layer, like if I have multiple layers here, let's say this is wood, this is some foam, and this is drywall, and this is the inside of the house, and this is the inside of the house, and this is the outside of the house. How is the heat going to go from here to here? This is the outside and this is the inside. How is the heat going to come from the outside to the outside wall?
Through convection.
And
then it's going to go through as
radiation.
And radiation. And then it's going to be
going through this first layer through what? What mechanism?
All the way through.
Conduction, right? And then once it hits this wall, now what?
Convective.
And
then if there's an object that it's going to radiate, then radiation.
Yeah. No, the wall will radiate. The whole wall will
emissivity, right?
Huh?
The wall would have emissivity.
Everything has emissivity. Even you and I have emissivity. There's no. I mean, everything radiates. It is just about whether it is significant or not. Okay. If these two are almost at the same temperature, then radiation is not that significant. Otherwise, it is.
Professor, in what situation would we use black box radiation?
Black body?
Or black body.
It has to be told to you explicitly that this is treated as a black body.
Okay.
Or if it says what is the maximum radiation what is the maximum emissive power? What is the maximum power that you can get?
Okay.
By radiation. In that case, yes, then the maximum means black body.
Okay. Thank you.
Any other issues with this?
Would the area count? Like, would you take into account the area since they're all the same?
Yeah, the area would still count. So your for convection, the equation is HA T hot minus T cold. For radiation, it is sigma A T hot to the minus T cold to the power 4. And for Q conduction, it is Ka T hot minus T cold over the thickness. So they all have an area term in there.
Because I noticed in one of the homeworks, it was 3 pipes connected to each other, and they had equal length and equal areas.
Yeah.
But in the solutions, it didn't account for the area.
See, sometimes I might have done this. I might have divided through by area because they're common. Sometimes they drop out because they're all common. But don't cancel them out before you do this. So first write out these equations, and then if they cancel out, then they cancel out.
Okay.
Okay. The area term has to be there.
All right.
Okay.
Sounds good. I think that's about all the questions that I have.
Okay. Then if you're done with this, then I want to go through a couple of questions, problems from energy conservation from the additional problems. Okay?
All right.
Okay. Then this is problem 15 from there. So it's a 0.5 kilo-pound block. So let me show you the picture. It's this picture. So there is a 0.5 block, 0.5 pound block, and it's first compressed against a spring and then let go. It goes up the loop and down. And the question is, how much should the compression be? What's the minimum compression that should be by which this should be compressed so that it doesn't lose contact anywhere?
Where is this?
This is the I think it's on the course material additional problems, or yeah, additional problems.
Oh.
What problem is it on? I forgot.
It's problem 14.
Okay.
Right.
Have you guys formulated the problem?
Mm.
0.33 feet? I don't know. Let me check. Yeah, correct. Good. Yeah. So how are you going to do? Okay, so walk me through the process for this. Okay, how would you start this?
I don't know.
Okay, what do you need to do?
I tried using energy conservation, but that didn't work. So I'm
So
guessing
okay, so what are you asked to do?
determine the stretch of the spring required to make the thing go around.
To make the thing go round. So what does that mean to make the thing go round?
You have to give it energy through the spring.
Uh-huh. For what purpose?
To make it go on the loop.
Uh-huh. So what would make it not go on the loop?
Slow speed.
What would happen?
It would fall down.
Okay. What does it mean to fall down?
Have a zero velocity.
No. Not zero velocity.
I don't know.
What would happen if it's going too slow along that curve?
It would
So
fall off.
let's say that this starts going up slowly.
Okay.
Okay.
It
And
would
if
reach height, then it would not have enough energy, so it would reach a height and then fall down.
okay, so if it's falling down, where is it going to fall down? Most likely, it's going to fall down somewhere up here.
Yeah.
So when it is falling down, what's happening to it? What does falling down mean?
Free fall.
No. Well, yes, but then what does it mean for the contact between this and the loop?
No contact.
No contact. What does it mean?
Normal force is zero.
Correct. Normal force is zero. So what you need to do then is to yes, normal force is zero. So so then if it's normal force is zero, then draw the free body diagram for it at the top at this point. Okay, let me write on this. So here is the block at D. What are the forces acting on this?
Weight.
Mm-hmm. And then?
Normal force.
Yeah. Actually, this way. Mm-hmm. That's it, right?
Yeah.
So sum of forces equals what?
0.
Is it an equilibrium?
Oh no, it would have a speed M1A.
So tell me the equation.
So it would be minus W minus Fn, or normal force equals 0, or equals M1A.
And what is A?
Acceleration.
Yeah, and what is it?
Oh, this is angular acceleration, so v squared over r.
Right. And this should also be negative, right? Because it's pointing down.
Yeah.
And we want n equal to 0, right?
Yeah.
Otherwise it'll lose contact. All right. So then G would be v squared over r. Okay. Or v squared would be rg. Right? Is that part clear?
Yeah.
Now, how would you find the velocity at this point?
You solve for it right there.
Okay. But then how would you relate the energy here to the spring compression? What relates this and this?
I think you can divide the sum of forces at the beginning by the sum of forces at D.
What?
No? Never
When
mind.
have you ever done that? Like take a force from one state and put it in the other and do it something with the other state. Whenever you have stuff where you have a beginning, something happens, and something going on at the end, then it has to be energy conservation.
Oh, so at this point now we can use total energy initial equals total energy final?
Yeah.
Because we have the velocity.
Yeah. So what is the total energy here?
Spring.
Uh-huh. And what's the energy here?
Potential and kinetic.
Correct. So you have kinetic plus potential here equals spring energy here. That's it. So you know the kinetic energy here, right? From this.
Yeah.
You know the potential energy because you know what this 2 is. This is 2. So 2 plus 2, 4. So you know this.
Yeah.
So you know the total energy here. Then you just have to equate it to the total energy here. And you know K. Once you know K is 1/2 K delta squared is equal to that energy. That's it.
But that's only like half of the circle.
Yeah, but then it's going to lose contact there. If it has enough velocity to go there, then it'll come all the way through. I mean, it's only going to fall up that point. If it makes it up here, then it'll make it all the way through.
Oh, okay.
Okay.
All right.
Okay, then do this one too. 15. Just walk me through the process. You don't need to do the whole thing. I want to actually do then the next two problems, the 15, 16, and 17, all the three. Got it? What's happening here?
Got it set up.
Yeah, just energy is sufficient for this. So what's the energy at point A?
Spring energy is 1/2 K delta squared.
And what's delta?
100 millimeters, 0.1 meters.
Correct. What's the energy at? So what did you equate that to?
I made it total energy at B.
Okay. What's the total energy at B?
There's kinetic and spring, and I was thinking maybe potential since it's lower
So why maybe?
because it didn't really give a 0 point, so I just made my own 0 point
Where did you put your 0 point?
on the top.
Okay. So then what is the formula? What is the total energy here?
Total spring, kinetic, potential.
And what are you doing with potential? Is it plus or minus?
It's gonna be minus because the height is going down.
Yes. Okay. Good. So very good. So then the spring is now what is the spring extension now?
0.050 meters.
0.005 meters. Correct. Okay. Good. So you got that right. So the total energy here is the total energy here, and then the total energy here is just the spring, and the energy here would be the spring plus potential minus spring minus potential because it's going down, and kinetic. Good. What's the energy at C?
So it's
Just talk about it. I'm sure you can do it. What is the energy at C?
Do we assume that it comes to rest at sea, or it's gonna?
No, it's going to keep going.
Okay.
Well, why does it have to keep going? Because look, the energy here has to be the energy here, right?
Yeah.
Here it is at rest and it is stretched. Here it is not stretched.
So it has to have some kind
So
of.
it cannot come to rest here. It has to be moving.
It's gonna be kinetic energy, and that's it. Just kinetic.
Yeah. So the spring energy here would be equal to the kinetic energy there.
Oh, you can do it from point A?
Yeah, because this equal to this equal to this, right? So this equal to this.
It would be the same thing if you did it from B then, right?
Of course, because A equal to B, B equal to C. So you can do A equal to C.
Yeah, it would be less work from A though, huh?
Yeah, because only one energy there, right?
Yeah.
All right?
All right.
Okay, then do this.
Number 16?
Mm-hmm. Okay. What is the how are you going to do this?
Do you start by finding the force that the package is going down?
Force?
The mg sine 20.
You're doing a force. You're using force method.
Oh yeah.
Okay. So then what? Okay. Then what do you do? Is it smooth? Okay? Then okay. Walk me through the process.
Oh okay. Well, I found the weight of the 50 kilogram
Yeah.
box, and then I got the force that's going down the 20-degree ramp, which is mg sine 20.
All right.
And I set that equal to the spring force.
How does that make sense? I mean, the box is here. The spring is all the way down there. You mean when it's already compressed?
Huh?
You mean when it's already compressed?
Can we find the velocity at the end of the 8 meters, and then put by using, so you put mg sine theta equals ma, and through the acceleration you can find the velocity by using v squared, bf squared equals v1 v initial squared plus 2as.
Okay, good.
And then make that energy at the bottom of at the end of the 8 meters equal to the spring energy.
The energy of what? Say what? Say that again.
The energy at the bottom of the 8 meters, and then put that like right before it hits the spring. And equate that to spring energy, and solve for delta, which would be 50 plus delta. No, it would be 50.
What problem are you guys doing?
This is problem 16 from the practice problems.
Ah, okay.
Can you do it that method, or?
So go on, finish it. Tell me what you did. So you're taking the energy here, right?
Yeah.
What is the energy at that point? What is the energy of the system?
It would be potential. I mean, not potential. This course spring energy and
Is it potential energy equal to spring energy?
Where potential energy where?
Of the box? Or is there more?
Okay, at what point? Here or here? Pick one.
The top.
Okay, you want this is this is your initial system, right?
Yeah.
What is the total energy in this of the system and in this state?
Is it potential energy?
Okay.
And spring energy?
Why?
Because the spring is already compressed.
Very good. So it has potential energy. There is potential energy. There is spring energy. What else? Is there any kinetic energy?
Yeah, 2 meters a second.
So it's already moving.
Oh yeah. Okay. Yeah, there's initial kinetic energy.
So it has potential, kinetic, and spring. And where is your 0 point? Where are you assuming your 0 to be for potential?
The height where the box is.
Here. This is your 0. Okay.
Yeah.
Then the potential energy is 0 then.
Oh wait.
I mean, if you assume that your I mean, it has potential energy, but it is 0 because you are assuming that to be a reference.
That would make it so the potential energy on the right side or final side is going to be negative, right?
Yeah, then if it comes down, it'll be negative. That's all.
Yeah, okay.
So then what's the final energy?
You're going to have spring energy.
Yeah.
We're trying to see how much it compresses, so there's going to be no, what is it, kinetic energy?
No kinetic energy, correct?
Since we made it so potential energy at the top is 0, then it's going to have potential energy at the bottom, which is going to be negative.
Correct.
And there's no friction, I believe.
There's no friction, right?
Yeah.
Yeah, there you go.
That's it.
I thought we can't use the total energy method if it's not constant acceleration.
You cannot use force method, not energy. Energy is very applicable.
Oh, wow.
Acceleration is related to MA, right? When you have energy, there is no acceleration. I mean, there is acceleration. I mean, you don't care whether there's acceleration or not. There's no such There's no term for acceleration there.
I was only doing the force method because I thought I couldn't use the energy method when you're
The other way around.
Yeah.
Okay.
So the equation is kinetic energy initial plus spring energy equals to potential energy plus spring energy?
Yeah. Yeah.
Okay.
Wait, can you write that down?
Well, yeah. So here it is the kinetic energy kinetic energy plus the spring energy. This is 1/2 k times 0.05 or something, right? What is it? How much is it compressed?
50 millimeters.
Okay. So then 0.05. And this is 1/2 m times 2 squared. That's an initial. And the final would be, so let's say that it compresses by x. Okay.
Okay.
So that would be the final energy would be kx squared. Actually, it should be 0.05 plus kx squared, right? It's already compressed 0.5 or 50 millimeters, and then there's an additional x, so it has to be plus x squared.
Yeah.
And then minus mg times 8 plus x, and then sine 20, because it is falling this distance.
Wouldn't it be easier to make the cable your 0 point, your origin?
Okay. Then you'll have this term go over to the other side.
Oh, it's still gonna be there.
It'll be there somewhere or the other.
Professor, what do you have as the answer?
I don't know. Let me see. I have it somewhere. 0.36.
Oof, I wonder what I did wrong then.
So this is what I did. Here, you can look at my.
0. what is the max displacement of?
The what?
You have a D2
That's
is equal to.
X. That's X. Sorry, this.
Oh, okay. Oh,
That's what
so,
I did here too.
so we're not stopping at the point where it's like halfway. We're going to the point where it goes past the amount of springs. It's gonna want to go back.
Yeah, because you don't want to, because there's no point in stopping here. I mean, you might as well just go all the way here to find. I mean, you can do one step. You don't need multiple steps.
Okay.
I'll post this tomorrow morning so that as soon as I get to my office.
Okay. How did you solve for X though?
Then just solve it. I mean, you'll get like a quadratic. You'll get a quadratic.
Okay. Yeah. Yeah. Okay. Right.
Okay.
Yep.
All right. So do this one. This one will take you a little longer, but it's but yeah, do that one, and then if you cannot do it, come to my office tomorrow.
Okay.
All right.
Yes.
Guys, any questions? I'm going to sign off in about 2 minutes.
Okay, so let's say you have a pulley system and you're trying to determine which way it's going to go, like if it's going to go to the left or if it's going to go to the right. How do you go about solving which way the masses are going to end up going?
Like what?
I can draw it.
Like this? Like that?
Can you move the paper up? Yeah, and let's say like there's a third mass there, so it's kind of like this.
Like this?
Yeah. How do you determine which way it's going to end up going?
It doesn't matter. Just pick one and then make it consistent with the rest.
Okay, and if you get a negative answer, that means
the A will come out. The A will come out positive or negative.
Okay, and if it's positive, you chose the right answer. If it's negative, you chose the wrong one.
Yeah.
Okay, thank you.
All right, guys. Anything else?
That's all that I got. You'll still have office hours tomorrow, right?
Yeah, but I might have it in the afternoon as opposed to the morning, because I might have something to do in the morning. But I'll let you know tonight. Okay.
Okay.
Okay. All right.
Thanks.
See you guys tomorrow.
Okay.
See you
Thanks.
tomorrow.
All right, bye.